All right, so like I said, let me say it again. We're going to continue what we did the last time, 6465 sampling distributions. But to do that, I was telling you guys I need to go to the website. And if you go into modules, and if you scroll down to the current module, unit 4, click here. Yeah, and so if you click on that link right here, go back. You click on this link right here, open stats book sampling distributions. If you click on that link right here, that will take you to this website right here, sampling distribution. And what I am going to do is click on begin up here in top corner right here. All right, and so you'll see this right here, this grouping right here of distributions. So this over here is what we call the underlying distribution. In this example right here, the underlying distribution is a normal distribution. Yes? From this normal distribution, for example, I can pick 5 people at random to make a group, right? So let's say you guys, I pick 5 and I get your scores. I can pick 5 people at random, yes? If I click on the, see right here, the 5 right here, click animated right here, 1, 2, 3, 4, 5. It took 5 people, and then it took the average of those 5 scores, and that gives me a score right here. All right? So the average of these 5 people is this score right here. Does that make sense? I can do it again. 5 different people. Again, you're picking people randomly from a normal distribution. So most of the people will come from the center, but every once in a while you get an outlier. Yes? You take the average and they added, now you see two dots right here. Yes? If I do this again, 1, 2, 3, 4, 5. See, this time I had an outlier. Somebody did really poorly on the test. And then so the mean is going to be a little bit small. When you take the average of these 5 scores, the mean is going to be a little bit lower than the other ones we had so far. Yes? Let's do it again. 1, 2, 3, 4, 5. And again, even with this guy way down here, the other scores kind of brought the mean up. And so this blue box just came right here. Now, if I keep doing this over and over and over again, this down here will follow a basic shape. Let's do it 5 times in a row. So I click 5 right here. So if I did that same process 5 times in a row, this is what I have right here. If I go again, hit 1, 2, again. If I keep doing this again, let's do it another 5 times in a row, like so. You can kind of see this kind of shaping up, right? Instead of doing 5, let's do it 10,000 times. So let's go basically 10,000 groups of 5. Yes? Let's do it 10,000 times right here. And you can see this shape is looking like right here. What does this shape look like? It looks like a normal distribution, yes? Right? But notice right here that it is not as wide as this original distribution right here. It has the same mean. So you see right here, the mean, they have the same mean, but this graph is not as wide as the other graph right here. Yes? I am taking a sample of 5 people, the distribution of the average of those 5 people right here, excuse me, that distribution is going to be normal. Questions there? Questions there? But here is the amazing thing right here. If I was to change the distribution, instead of it being normal, let's make it in, for example, into a uniform. You guys know what a uniform distribution is? Mine is almost uniform. A uniform distribution is basically it's flat. The probability is that you get a person is simply random. It's the same probability that someone gets 0 as somebody gets 100. It's exactly the same probability. We call this a uniform distribution. So if I start again, and again, you take 5 people at random, they're just going to show up anywhere, yes? Get myself an average of these 5 scores at this score again. If I go ahead, 1, 2, 3, 4, 5, get an average, score is right here. Again, if I take an average, 1, 2, 3, 4, 5. But you get the idea, right? From this group, I'm pulling n equals 5. I'm taking 5 people and I'm taking the average score. Yes? What would happen if I do this 5 times, 5 times, 5 times? If I just skip, let's do it 10,000 times right here. watch what happens. What does this distribution look like? The one in blue. This is the distribution of means. This is the average of those 5 people. What does it look like? It still looks normal, yes? Yeah. Let's say I had a different distribution. So let's start again. If I had a distribution that looks like this, you're more likely to go like this, and then you kind of taper off as you go like so. This is a distribution, for example, that's for light bulbs. Most light bulbs will burn out quickly, but a few of them will last a really long time. Yes, this is the kind of distribution that you see for your light bulbs right here. You know, you have a few light bulbs that keep going forever, but most of them will burn out after a few months or so. Yes, distribution right here. So again, if I again put 5, 1, 2, 3, 4, 5 average, most of the scores will come from over here because this is what's more likely to happen. Yes, but if I keep doing this 1, 2, 3, 4, 5, and then take the average, again, if I do this 10,000 times, what does this distribution look like? It's looking normal. Yes, if I do it 10,000 times. Right? If I do 10,000 times, it still looks normal, yes? If I made the overall the underlying distribution, if I made this underlying distribution just crazy, up and then down, up and then down, up and then down, up and then down. So this right here, this distribution is more cyclical. It's kind of like how much money you have in your pocket, the probability based upon time of the month you've gotten paid. You have more money at the beginning of the I guess you get paid in the middle for this one. Middle of each month you get paid, so you have more money right here. And again, if I run this distribution 10,000 times, look at the underlying distribution. The underlying distribution is still normal. Yes. So literally, it does not matter how the group's probability works. So for example, in this class right here, this is what the probability for your scores in your test. Just test scores probability looks like this. Very low, and then when you get to about 80% are really high, and then it tapers off like so. This is what the probability for a test in this class looks like. Most people score between 70 and 80% on the test. Very few people do badly, and very few people get 100. Yes? That's what the distribution looks like right here. But if I start taking groups of people, then the distribution of the averages for students will, let me clear the lower through again, clear the distribution right here, will still be normal. Okay? And this discovery shocked the world because the simple question is, why should it be normal? Shouldn't this, how the numbers up here dictate how this behaves? And the answer is no, it is not. It's one of the fundamental properties of our universe. You know, our universe has lots of fundamental properties, right? Right, the speed of light is a fixed constant. Yes, there's Avogadro's constant in chemistry. The number of moles in a certain amount of weight of items is always the same. No, there's tons of just constants. Now this is one of them, right here, and this is why distribution is called a normal distribution. Everything becomes normal once you start looking at the distribution of its means. Questions there? And that's what I was trying to explain last time. I don't know if I did a great job of it last time. I got my fingers crossed. So the sampling distribution of the sample mean, if you try and figure out how do means behave, the sampling mean right here is, remember we did a while ago, you took 5 people, you got the average, you took 5 people, you got the average, you took 5 people, you got the average. If you want to understand how those means behave right here, is they follow this simple process right here, is that the average of the mean of the overlying database is the same as the average, the mean for the let me just show it to you this way. There we go. See right here, this distribution right here, the mean for this distribution is right here. The mean for your underlying distribution is going to be the same. So if I reset, if I make this a normal distribution right here, and I do this 10,000 times, 10,000 times right here, you see the mean right here? The mean for this distribution is going to be the same as the mean for this distribution. The mean for the individual person and the mean for the groups of people, those two means are going to be the same. Okay? What's going to change is the standard deviation is going to change. The standard deviation, I lost my page. The standard deviation is going to be the standard deviation for the individual divided by the square root of n. And so the standard deviation for the sampling means will always be smaller than the standard deviation for the individual person. Questions there? Questions there? All of this is provided. So like they say, like we did one example of the skewed. Even if you do a skewed right here, the underlying distribution was still going to be normal right here. And this process right here goes through something called the central limit theorem. This right here, again, remember I said the underlying theory is always true? This is the name of the underlying theory. The name of the underlying theory is called the central limit theorem. The central limit theorem says that it is a remarkable fact that the sampling distribution of means is always approximately normal for a large sample from any distribution. Questions there? So again, it does not matter how this is distributed up here, any distribution right here. If you look at a large sample, if you look at a large sample, the distribution of the sample means will always be normal. Questions there? The name of this process is called the central limit theorem. What happens is that the means become normal. Okay, the requirements to meet the central limit theorem in most circumstances is that your sample size needs to be 30 or larger. So if I take a sample, aim to take a sample of 30 people or more, then the distribution of the average will be approximately normal. Questions there? This process right here is used all the time. Have you ever had, we're approaching, we actually just started last week, campaign season, right? We're pushing campaign season. You ever watch the TV shows or whatever, and they say, hey, this person right here, this is his support. He's gaining 48%, and this person over here, he's gaining 28% of the support or whatever. Yes? Yes? This is how they do this process right here. They sample like 300 people, and then they extract the distribution of the means. Because what they're doing is the average support, yes? On average, 48% of the people support person A, 20% support person B, yes? But notice right here, they can do that without going deep into your lives. They just call you on the phone and say, hey, who you gonna vote for? And then that's it, right? The way that this works right here is because it doesn't truly matter how people are distributed within the community, right? Because, maybe one side of the community has more favor than the other person, and another side of the community maybe favors the other person. That doesn't matter. How they're distributed does not matter. Once you get a large enough sample, the numbers you get will hold. Questions there? That's one of the most basic underlying of modern theory in terms of statistics, in terms of almost anything that you do, right? Like a football game. When they go to a football game, they don't just buy 7 billion sodas to make sure everyone has something to drink. That's not what they do, right? They look at samples from either our stadium or from other stadiums on how much sodas people drink, and they use that to get an estimate of how much sodas they'll make. They'll need, right? Right. Same thing with your car. They say your car needs to go 3,000 miles before it needs an oil change, right? They didn't go ahead and run 60,000 cars. They just ran 30 cars and looked at how they used up oil, how the oil was after those 30 cars were used for 3,000 miles, and say, okay, at this point the oil needs to be replaced. Right. That's what they did. They didn't just randomly guess at 3,000 and cross their fingers. That's why some cars can get up to 6,000 miles before the oil needs to be changed. They did the math. They did the statistics. All right. So once your sample size is greater than 30, then the mean for that distribution is approximately normal, with the means being the same, but the standard deviation changing to sigma divided by the square root of n. Questions there? Now there is one caveat to this process right here. Remember how I said that the you need a sample size of 30 to make this work right here? If the sample size is 30 or larger, then the central limit theorem applies. There's one time when that's not the case. If the underlying distribution is already normal, then this becomes 1. Sample size of 1 or larger will work. And so that's what they have right here. If the population itself is normal, then the sample mean X bar will already be normally distributed. The sample size can be any amount, 1 or larger. It does not matter. It will automatically, the central limit theorem will automatically hold. Questions there? All right. So, example 1. A sample size of 45 will be drawn from a population with a mean 15 and a standard deviation of 35. Is it appropriate to use the normal distribution to find probabilities for averages of sample averages? And the answer is, oh man, I touched it, didn't I? The answer is yes, because the sample size is greater than 30. Okay, notice right here, they didn't tell you how the population was distributed. This population might be skewed to the left. This population might be normal. This population might be geometric. This population might be a Poisson distribution. This population might be uniform. They didn't tell us anything. Once the sample size is greater than 30, automatically the central limit theorem will hold. Yes.
What is geometric distribution?
A geometric distribution is a multiplicative distribution. And so what happens is if you have, say, for example, say 20%, then the next will be, say, for example, half that amount, and so forth and so on. So geometric, you're multiplying to get the next value in your distribution. An example of a distribution blue theory right here is you're rolling a die and you try and predict how many times you get 5 in a row. That will be a geometric decision because each time you roll it, you multiply it to get the next probability. Anybody else? Example number 2. You have a sample size of 8 that will be drawn from a normal population with a mean of -60 and a standard deviation of 5. Is it appropriate to use the normal distribution to find probabilities for X bar? Yes or no? Yes or no? So the first thing we'll do is we'll check the sample size. Yes, the sample size is, that's no good, right? It needs to be 30 or larger, right? But they said that the population is, if the population is normal, we have to revise the sample size has to be 1 or greater, yes? And so therefore, the answer in this case is going to be yes. Since it's normal, X bar itself will also be automatically be normal. Question there. Question there. Example number 3. A sample size of 24 will be drawn from a population with mean of 35 and a standard deviation of 1.2. It is appropriate to use a normal distribution to find probabilities for the average. And the answer is? The answer is no, it's not. I needed a population size that's greater than 30 or the underlying population being normal. Questions there? Yes. So the problem for both of them is too small. Yes, the last one was 8. Yes, but in the last one they said the population distribution was normal. Sorry, on the wrong direction. In the last one right here, the population was a normal population. That overrides. For a normal population, this becomes n greater than 1. One or more is fine. Okay. Yeah, we just did this one. All right. So from here on out, we're just going to be practicing questions. So let me ask again, any outstanding questions about the distribution of means. The distribution of means come from the idea of something called the CLT, the Central Limit Theorem. The Central Limit Theorem says that for any distribution whatsoever, if you take a sample from that distribution, and if the sample size is 30 or more, then the average for that distribution will be normally distributed. Okay? And so one more time. So you go right here, I have this distribution clear right here, clear? So again, in this example, we're taking groups of 5. I can change it, If I change, for example, let's say 10 right here, and I hit animate, it'll take 10 items from this right here, and then take the average. See the blue dot right here? That's the average. Okay? Again, if I run it again, it'll take 10. Again, it's a random sample. So I'm selecting 10 people at random, and I'm taking the average. What we say, if I did this 5 times or 10,000 times, what we're saying is that the distribution of the averages will look like a normal distribution. Remember the blue are your averages? The distribution of your averages will look normal, i.e., most of the scores are at the center, and then it tapers off as you go from left and right. All right? Questions there? The means will line up. See right here, the mean for this distribution right here is exactly the same as the mean for distribution right here. The two means will be the same. But what will change is the standard deviation. This distribution right here has a standard deviation of 9.4. This distribution right here, the standard deviation will always be smaller. Standard deviation for this one right here, the standard deviation right here is I just changed slightly, but it was 9.4. I touched the screen. Put it back. The distribution is about 9.4. The distribution right here for the means, the distribution of the means will always be small. And the way you calculate it is you take this score and you divide it by the square root of n. In this case, n was 10, correct? Yes? And so if I take 9.4, so if I take 9.4, and I divide it by, open parentheses, the square root of 10, because there are 10 people right here. Enter, right here, see the 2.97? See the 2.97? 9.4 divided by the square root of the sample size. Now I have 10, I'm taking 10 dots at a time. Yes? That gives me an answer of 2.97. That 2.97 is going to be approximately the actual standard deviation for the distribution. Questions there? Questions there? And this works anytime, and this works, it does not depend on your underlying population. Your underlying population can be normal. Your underlying, I can hit normal, this uniform right here, skewed to the left. Normal, your underlying population is normal. It does not matter. It calculates exactly the same. Questions there? And what that therefore gives us is power, because that means I can control the distribution. I can take any distribution I want, and I can force it to be normal. All I have to do is take samples instead of just taking one person at a time. Questions there? All right. So like I said, that's the theory. Now we're moving into more practice. The first thing we want to define for you right here is an unusual event. For us in this class, an event is considered to be unusual if the probability of it happening is less than 5%. Okay, that's just a definition you have to memorize, right? So the question asks, is it unusual for students to score less than 20% in my class? You just need to find what's the probability that you score less than 20%. If that number is less than 5%, then you say it's unusual for that to happen. Questions there? An unusual event is one that is not likely to happen. There's a cutoff. That cutoff is 5%. If the probability of the event is less than 5%, we say that is unusual. Okay? So if you go to McDonald's, you know they have those fancy machines that just automatically put the juice in the cups. So when the person is putting in the order, the cups just fall and the juice falls in the cups, and it's all done all automatically now. Yes? There's less than a 5% chance that it will spill the juice. So it's unusual that the juice will spill, or will put too much drink in there. Questions? That doesn't mean it never happens, right? If there's a 1% chance, means every 100th drink someone's going to get a spilled drink. Yes? But it's just unusual, unusual, it's unlikely. All right. We've done these before. Between button, less than button, greater than button. We know how to use all these in SALT. We'll get to that in a second. But let's look at our first example. Based on data from the United States Census, the mean age for college students in 2011 was mean of 25 years with a standard deviation of 9.5 years. A random sample of 125 students is drawn. Now, that's my first point I want to make right here. In the previous sections, 6.1, 6.2, and 6.3, this part of the question is not there. In the previous questions, the question was simply, what's the probability that a person or a student is greater than 26 years? It was, what's the probability that a student is greater than 26 years? That's the question that we've been asking in the first three sections. All right? But now we're moving into a different world where what we're doing right here is we are taking a sample, 125 students. We spoke to 125 students and we asked them, how old are you? Okay. And so the question is, what is the probability that a group of 125 students will have an average age that is greater than 26 years? All right, different question. So that's what's the probability that the average for the 125 students is greater than 26 years? Do you see the difference between the two questioning sets? One of them, we're looking at a sample and we're asking you about the sample. What's the probability that the average age for a group of 125 individuals is going to be greater than 26? All right? That's different from picking a student at random. What's the probability that that student is greater than 26 years of age? All right? So, again, previously, I guess I should put this previously over here. Probability X is greater than 26. X right here follows a normal distribution with a mean of 25 and out of space, a standard deviation of 9.5. X bar over here will follow a normal distribution with a mean of 25, but the standard deviation is going to change. I am not going to use 9.5. I'm going to use 9.5 divided by the square root of 125. And that's the key change right here. Remember I pointed that out? The means are the same, but the standard deviation for the blue distribution is always smaller. Yes? This right here is our blue distribution. And so the standard deviation is not 9.5. It is 9.5 divided by the square root of 125. Questions there? Questions there? Right? And if you recall, I showed you the picture. What happens is that the blue is always more compact, right? Because as looking at the averages, those tend to be fall near the middle. Questions there? All right, so first things first, you have to check to see if the sample size is large enough. Is 125 larger than 30? If it wasn't, we just couldn't do anything. Literally, you just say for that question, that's the kind of question you dream for. You dream about, you simply say, the CLT does not apply, and then you move on. Because you don't have the ability to solve the problem. But of course, we ain't gonna never give you that in the test. That's just too easy. Yeah. But what was I not supposed to say that out loud? That we make the test hard? Was I not supposed to say that out loud? Yeah, but like 99% of the questions you get, the sample size is gonna be big enough, or the underlying population is gonna be normal. So you can use the CLT, right? And then from there, we just go ahead and we find the probability. The mean is going to be the same, just like I said a while ago, right? But the standard deviation is not 9.5, it is 9.5 divided by the square root of 125. All right, let's go ahead and solve this in SALT. So, how'd I get to my good friend SALT? Oh, there he is. Hey, he reset for us. Lovely. All right, so first things first, the mean was 25 years of age. The standard deviation, oh, it's not 25. The standard deviation was, we don't know, so we have to calculate it. We have to go clear. There we go. We have to go 9.5 divided by the square root of 125. Like so. That answer is 0.8497. Now I'm going to tell my students to take it to 4 decimal places. 8497. And so I put that in there, 0.8497 right here. I choose a right-tailed test. And I plug in the box, 26 years old, I believe it was. Plug in the box 26. And there you have it. There is a 12% chance, 11.96. There's about a 12% chance that a group of 125 students, their average age, it will be greater than 26 years. Questions there? Comments? Queries? Concerns? Don't worry about a thing. Cool. And so, of course, they do it the hard way because, again, we don't have to find the z-score. But by the way, SALT does find the z-score for you. Again, you can look down here for an estimate for the z-score. It's approximately a little bit more than 1 standard deviation above the mean, but you can also see that it calculates the z-score for us, 1.1769. But again, we don't have to calculate any z-scores. We don't have to do any of that right here. And again, see, they got the same answer for us, about 12%. Question there. Question there. Now, for these kind of questions, your rounding is very important. Excuse me. You should try to avoid rounding until you have to. Like I said in SALT, when you put the standard deviation in there, put that to at least 4 decimal places when you put that standard deviation there in SALT. All right? All right? Cool. Cool. So I should let you try one. All right. Hereford is one of the most popular breeds of cattle. Based on the data from the Hereford Cattle Society, the mean weight for a 1-year-old Hereford bull is 1,135 pounds, with a standard deviation of 97 pounds. Would it be unusual for the mean weight of 100 heads of cattle to be less than 11,000 pounds? See if you can get that answer in SALT for me, please. See if you can get the answer for me, please, using my good buddy salt. You can just go to Google this type of salt and then engage. That AL students engage, and those should be your first thing pulled up. So I'll put you mark it for your test. I'll make so much easier to find it when taking test. Anybody need more time? Are we ready? Ready?
No.
No, okay. Anybody need assistance? Anybody need help? Okay, we think we got it. Right, so first things first, you should always find n first, and that separates the two questions. Where from 6.1, 6.2, 6.3, there is no n because the sample size is always 1. And so the first thing we need to do is identify n. What is n? What is n? 100. So we're looking at 100 heads of cattle. So is that larger than 30? That means we're in business, yes? All right. And so therefore, X bar, the average weight of 100 head of cattle follows a normal distribution. What's the mean going to be? What's the mean going to be? 1,135. And what's the standard deviation going to be? It's going to be 97 divided by the square root of 100. Yes? Questions there? Square root of 100 is 10, so this is 9.7. Is that okay? And then the question is asking, what's the probability that a group of 100 cattle, the average weight is going to be less than 1,100 pounds? Questions there? So if you didn't get it the first time, do you think you can put it now in the salt and get the answer now? Can you put in salt now if you didn't do it before? You think you can get it now? What's the probability, somebody? So what answer did you get, somebody? 0.0002? I'm missing a 0. Is that what we got? I'm missing a 0? I can squeeze it in right here. Is that what we got? Yes. I mean, I'm about to show you, but yes. Okay, well, let's do it together then. So we come over here, right here in salt. I put in a mean of, what comes here for the mean? I forgot already. 1,1130. What comes for the standard deviation? 135? What comes for the standard deviation? 9.7, not 97. Yes? 9.7. Yes? That's the main place to make the error. Is it a left tail test or a right tail test? Left tail test. And I want the probability that it is less than 1,100. Yep, I switched guys in all them zeros. Yes. So to 4 decimal places, 1, 2, 3 is 0.002. Questions? Comments? Queries? Concern? Cool. And of course, you can see right here, only a small part of the graph is shaded. The average is 10 1135, but because the standard deviation is 9, it takes a lot of jumps to get all the way down here. Okay, so normally right here, if a farmer weighs 100 head of cattle and he comes back with this weight, right? This low weight right here, normally that indicates to him something is wrong, right? There may be disease going through the cattle that they're not aware of. There may be the places that they're grazing them, the grass itself might be might having some kind of disease, and that's causing not to be as nutritious, right? Could be weather related, could be other things that's going on, right? That's one of the things that farmers do right here is they would regularly weigh their animals and then look at them as a group. We try and figure out if something going on that we're not just seeing. The statistics are saying, hey, there's an alarm here, something's going on. You need to go ahead and try and figure out what's going on. Yes? Questions? Comments? Queries? Concerns? And so a sample size is 100, that's greater than 30. So we're in business right here. And so we just plug in the mean and the standard deviation. Again, 9.7. By the way, the results will be very, very different if you use 9.7. 97, sorry. The results will be very different. Yes? And then, again, we don't have to find the z-score, but that's the z-score right here. Notice a very small area is being shaded down there. And so 0.0002. Questions? All right, so I believe that in class on Friday, we will work on the in-class assignment. I think you have to do questions from, I have selected questions from the entire chapter that I want you guys to work on, the more interesting questions. All right, that's what we'll do on Wednesday. Technically, we're finished with the material, so I'm going to make Friday optional. I will be here on Friday, and so if you're here on Friday, we'll practice. We'll just do examples. We'll have a good time doing that. Yeah, yeah, yeah. You know, if your ride is not leaving until Friday afternoon anyway, so you can just come and hang out with us. Just, but it is off. Questions. The test. The test is going to be on Wednesday when we come back. I don't want to make the test the Monday after spring break. So the test is going to be the Wednesday after spring break. All right. Questions there? All right then. You guys have oh, let me take attendance.